Beata. Beata is with us since September last year as a project leader for the ion beam facility. Beata has received a PhD from the Max Planck Institute for Plasma Physics in Garching, and the title of her thesis was Deuterium retention in carbon and self-implanted tungsten, so very relevant for us. After her PhD, she stayed at the Max Planck Institute, where she also did some work on tungsten as a plasma-phasing material for fusion reactors, and also used there a lot of ion beam analysis techniques like Rutherford Backscattering spectrometry. I'm looking at all the comments. See, okay. Somebody can't hear me.
But I can hear you, Hans.
Okay, so I continue. Where was I? Yeah, she used a lot of ion beam analysis techniques. After Garching, she went to the University of Wisconsin in Madison, where she also directed an ion beam facility. So we are very glad that Beata was able to join us, and she will now talk about what can the ion beam facility do for you. And I think I'm confident that she hopes to spark your enthusiasm to do more with the ion beam facility we have currently at IBA. So Beata, the floor is yours.
Thank you, Hans, for the...
One remark that I should have made. We are recording this webinar, and this is a legal requirement that I inform you of that.
Okay, thank you, Hans, for the introduction, and Marco for sharing. Welcome, everyone. Today I would like to talk to you how you can use the ion beam facility for your research. But before I start, I maybe explain what you see on my title foil. So here, this orange picture on your right side, which you can see, this is the inside of our accelerator. This is the singletron power supply with the corona rings, and here you have the diodes. So we had recently a professional photographer who took pictures of our facility, and you will be able to enjoy them in my presentation. Okay, so first of all, so what is the purpose of this presentation? I would like to provide you with some basics of the ion beam analysis. Very little physics, just to spark your interest, and there will be more courses. I plan more seminars with in-depth physics for those who are really interested in those techniques. I hope that at the end of this presentation, I will encourage you to consider using ion beam facility so that you come to me, so I can evaluate your research project and maybe find place for IBF in your research. And then the second purpose is that I want to refurbish one of our chambers, and in fact the entire beamline. And I hope I can gather some feedback from you in terms of what you would like to study, so I can make this chamber as versatile as possible to fit your needs. So few words about our ion beam facility. So we are hosting 3.5 megavolt singletron accelerator from HVE. Is a Dutch company which produces those accelerators. There, in fact, are in the world 2 companies producing accelerators of this size. One is in the Netherlands, and the second one is called NEC in the US. And so we can produce maximum 4 mega electron volts for helium-2+, but usually we operate with energies 2 to 3 mega electron volts. Our accelerator can produce only gas ions, So unlike tandem accelerators, we cannot produce solid ions. And the gases which we are currently using are hydrogen, deuterium, helium-3, and helium-4. A very specific thing for our accelerator is that we can produce high current beams of hydrogen and helium, which means we can use this accelerator not only for the ion beam analysis, but also for ion irradiation. And we have 3 beam lines. One of them is TIAC, which is an ion beam analysis, in situ ion beam analysis chamber connected to the magnum chamber. So you can expose your samples, for example, to plasma, and then without breaking vacuum transfer them to a TIAC chamber and perform the in situ IBA. Then, this is that line here on your left side. Then in the middle we have the UPP beam line. The beam line has been already constructed, but let's say it's still not operational, but I hope this will happen this year. We already have scheduled some primary tests. And in UPP, you will be able to expose your samples to plasma and simultaneously perform IBA, which will make it a second facility in the world of this type. But compared to the other one, which is called, located at MIT, we can operate at higher plasma densities. And the third line on your right side, that is connected to a chamber which we call IBAS, where you can perform ex situ ion beam analysis and ion irradiation. And I think that beam line will be also open for external users and should also spark some interest. As I said, we can perform ion beam analysis and ion irradiation. For the ion beam analysis, you use it if you want to perform, want to measure elemental composition of your sample and perform some depth profiling. And this method is a quantitative without standards. With our current error bars are about 5%. But we could tweak it down to 1%. It is a non-destructive method. It doesn't require any sample preparation, and it's essentially fast and cheap if you don't consider the cost of the accelerator itself. It can be used in about everything. Therefore, I cannot imagine there is no application in solar fuel. So far, we have no solar fuel users, but since it has such broad applicability, I think it is possible that we could use it for solar fuels as well. And the other application is the ion irradiation or implantation, which is mainly used to create defects and modify materials. So typical applications are when you want to use ions as proxy for neutrons, for example, fusion-fission neutrons, or as proxy for cosmic rays, which are essentially protons, in field programmable gate arrays or in diamond detectors. Or, for example, you would like to change DNA of a plant or perform implantations in semiconductors. So this is a little bit about our ion beam facility. Now, I would like to talk a little bit more in details about ion beam analysis techniques, just little physics, not to overwhelm you. So the most basic ion beam analysis technique is called Rutherford Backscattering, and it is based on the Ernest Rutherford experiment from, I think, 1905, when his student was exposing gold foil to helium beam and noticed that some of those helium particles were backscattered. And this experiment served then later as an explanation for the new atom model. So you use this technique mainly in samples when you have heavy elements in light matrix. For example, tungsten on carbon. Here you have a drawing of it, more or less what it should look like. We have a beam coming from the accelerator. It is backscattered from the sample. Here we have light matrix, let's say carbon, and the orange particles are, for example, tungsten. And this is more or less a spectrum which you should register. So here the gray is again light matrix, and then you have a heavy orange peak coming from, for example, tungsten. So you can use this technique to simultaneously detect many elements to perform depth profiling. It has a very high depth resolution, even down to 5 nanometers. It is very sensitive, especially for high Z elements. Within 5 minutes, you can have millions of counts from high Z elements, so therefore you can go to low ppm detection levels for those elements. Sort of opposite to RBS, one moment, there is still RBS channeling. So there we also have RBS channeling, which is more or less the same, just instead of polycrystalline sample, you are using single crystal samples. And simply as it is shown here, if you have a single crystal sample and you will align your beam such that it can go into your channels, then if there are no defects in your sample, then you practically don't register any spectrum if your beam is perfectly aligned with your sample. If there are any defects, then you should see a higher signal, but still lower than compared with polycrystalline sample. We have a goniometer in our IBAS chamber, so we are technically speaking able to perform channeling experiments for you. Thanks to channeling, you can check the degree of damage and the amorphization in your sample. Then we have a technique which is called nuclear reaction analysis. It is sort of opposite to RBS. NRA is used if you want to detect light elements in heavy matrix. That, for example, would be deuterium in tungsten, which is depicted on your right side. So we have this orange is our heavy matrix. Light particles are, for example, deuterium. And then we have this black incoming beam from the accelerator, but in this case there are no backscattered particles. The beam which we are registered, this is not the original beam which we used from the accelerator. Those are particles coming from the nuclear reaction. And the typical NRA spectrum looks like this. We have a heavy signal from the heavy matrix, which in fact we can also remove if we use foils in front of our detector. And then we have peaks from our light elements. If we would like to perform this experiment using RBS, then our spectrum would be overwhelmed by the signal from the heavy matrix, and we would barely see the signal from the light element. So RBS cannot be used in this case, simply because, heavy particles cannot be backscattered from lighter particles. That's the reason why we cannot use RBS in this case. So NRA is used mostly for low Z elements, maximum to mass 15. You can use it to trace impurities like, for example, oxygen and nitrogen. It's also isotope sensitive, so you can see, I don't know, carbon 13, carbon 12, if this is, if you are interested in it. Then there is no high Z background, because here that background we can actually remove. It's true it requires expensive detectors, and it also needs, you need to measure cross-section. If you have some more exotic applications, then I would have to first measure cross-section for you to be able to perform those experiments. Then we have another technique which is called elastic recoil detection, and that one is used for light element profiling, mainly for profiling of hydrogen and deuterium. And so again, we have a heavy matrix and light particles in it. And then we have an incoming beam, but it's not this time, it's not perpendicular to the surface anymore, but it comes under a grazing angle. And what it does is just simply kicks off hydrogen atoms from the sample, and those recoils atoms are being detected. And so you then can measure you can measure the hydrogen and deuterium mutation. It's actually simpler than an array, and you can perform multiple element depth profiling. However, because the beam is coming under a grazing angle, the depth of penetration is very shallow, so you can only do maybe analyze like half a micrometer of your sample. And then still some assisting techniques. One is particle-induced X-ray emission. Simply when a beam is entering the sample and is coming by atoms, then the electrons are getting excited, and then mainly K and L shell electrons are being ejected from the sample, and then electrons from the outer shells are trying to fill this gap and falling to the lower shells, producing X-rays. And those X-rays are characteristic for each type of isotope, and you measure those X-rays, and this is how you use it in this technique. So you can detect multiple elements at the same time. This technique has a very high signal to background ratio. It's non-destructive, it's very sensitive, so you can even go down to 1 ppm sensitivity when detecting your elements. We have this technique available in our IBAS chamber, so you can, for example, perform RBS, NRA, and PIXE together, or you can perform ERD-RBS and PIXE together. And then we have also another technique, PIGE, which is particle-induced gamma emission. And it more or less works like an array. You again have nuclear reactions, but here in this case, the product of those reactions are gamma rays instead of particles. And again, you can those gamma energies are those are characteristic for every isotope, so you can detect different isotopes in your samples. And as I said, we have this available in our IBAS chamber as well. Okay, so here are the IBF parameters which we have at differ. I think we have them on our website as well. So as I said, we can the plus of the RBS, it's a very high depth resolution. The NRA, PIXE, and ERD can detect isotopes, especially PIXE can go to very, very low ppm values. And then the depths which we can sort of analyze, this of course all depends on the type of ions you use, on the type of target you have. But with RBS, we can go up to maximum 120 micrometers. And for irradiation, we can go even 150 micrometers if we irradiate light targets with protons. So is the question now, so how do those techniques compare to some other techniques which you can use for material analysis? So compared to other techniques, IBF, it's a non-destructive technique. For example, I think maybe some of you are familiar with SIMS. It has information depth larger than the other surface techniques, because we are using high energy beams. We don't need standards to quantify the data, and it can have a very high accuracy down to 1%, although currently at our chamber we have about 5% for RBS. I always get a question, or often, how does RBS compare specifically to SIMS? So here you have a chart which shows the detection range and analytical spot beam size for various material characterization techniques. And here we have RBS, and here is time of flight SIMS or dynamic SIMS. Also, when we compare RBS to SIMS, RBS is definitely a quantitative technique, which SIMS is not. RBS is also non-destructive, and SIMS is. You have a larger beam spot, which for some people it is to advantage, for some not. But actually for RBS, you can also have microbeam experiments. This is not the case in our chamber, but could be something in the future if there is interest for it. RBS is definitely faster than SIMS. Usually you need 5 to 10 minutes per beam spot, and it's definitely more accurate in terms of depth profiling compared to SIMS. Okay, so
Beata, we have a question from Richard.
Sure.
He wants to know if RBS really is non-destructive. He also understands that this is not the case, for example, for polymers or biological samples. Could you reflect on that?
Everything depends on the beam current. So for polymers or very delicate samples, indeed, you would have to use very low beam currents. And of course, it's also the amount of fluence. Shorter measurements. Yeah, I mean, okay, so at the end, RBS, can be a little bit destructive, right? But if you have shorter measurements, so less fluence and very low beam current, then there should be no problem. We, for example, analyze very delicate membranes. I'm talking few tens of nanometers, butterfly thickness, and well, they survive. There's no problem. So everything depends on, well, the experiment can be adjusted to your needs.
Okay, thank you. Is this okay for you, Richard? See what he... I suggest you continue, Beat. If Richard has more questions, we will come back to that.
Sure. So now I will just show you some research examples for ion beam analysis. Those are mainly coming from our facility. Usually for some of our scientists, there are some which them are not big performed from ASML, so I had to cut down a little bit on what I'm showing you because this is proprietary data. So sometimes I just simply constructed a similar case to show you what kind of research can be done. Okay, so case one, we use currently mostly ion beam analysis for deuterium depth profiling for diffusion purposes, and so we use generally this nuclear reaction analysis. Our beam coming from the accelerator is free helium. We want to detect deuterium. What we measure are alpha particles and protons. So when we perform this experiment in tungsten, then our penetration depth is maximum 4.5 micrometers. But for example, WEI is performing deuterium depth profiling in lithium. Then you have a maximum penetration depth of 45 micrometers. The very specific thing about this reaction is that it has a very broad resonance cross-section, which enables us depth profiling. This is also very fast technique. We usually spend like 5 to 10 minutes per data point. And as an example, here you have samples from Henny, which those are tungsten samples on various, usually on various substrates. And as you can see, those red points here, those are different data points on different samples. And then we have also green data points. Those have been measured at our facility. The red ones were measured at IPP Garching. But all in all, I would say there are about 100 data points here. And I think I measured all of that within one day. This is how fast this technique is. And thanks to it, that it is so fast, you know, I can, for example, since I collect the data across the entire sample, I can say, for example, whether deuterium plasma exposure was uniform or not. Is there any flaking, change of the coating flaking along the sample, etc. If this would have been a slower technique, I just wouldn't be able to collect all that data. And quite frankly, analyzing this data takes me longer than measuring it. Okay, and this is still the same example. I will be now talking about Henny's samples. So The objective for him was to measure deuterium retention and deuterium depth profiles in those tungsten samples exposed to magnum plasma. And here on your right, you can see one of the plots I prepared for him. This is the deuterium concentration versus depth in so-called thin film units. But here on the top, you have it converted into nanometers. And then we see the deuterium depth profiles at different positions from the center of the sample. I usually measured 7 points per sample in a distance of 4 millimeters. And then we can see how those deuterium depth profiles are changing. Here, those layers, frontal layers, are deuterium retention in tungsten oxides. Then we have deuterium in tungsten, so it is lower. And then we can see that in the molybdenum substrate, we practically see no deuterium at all. And thanks to the fact that I was able to collect so much data, as I said, I can also see the uniformity of deuterium retention across the samples. So this you can see on this plot. Here we have deuterium retention up to maximum almost 3 micrometers, which was the penetration depth of the beam for that experiment. And here we have the distance from the sample center, and again, more or less 7 data points per sample. And here, for example, you can easily see that for the porous samples, the deuterium retention is more or less uniform across the entire sample. But for the columnar tungsten, you can see that usually somewhere in the middle, the deuterium retention is the lowest, and it's somewhat getting higher on the sides. Now it's the question, is this the effect of the temperature, or that could be maybe oxide formation? This still has to be analyzed. And then again, because I collected like about 100 data points for all of those samples, here I can now, I have like more statistics to show, to be able to analyze different effects. So what you see on this plot, you have average deuterium retention from each sample, and here are the different sample names. They form 4 groups. Here the yellow group are tungsten. This is tungsten on tantalum substrate. Here we have the blue group is the pure tungsten. The pink group is the porous tungsten on molybdenum substrate, and then we have the green group, which is the columnar tungsten on molybdenum substrate. So when we look at the retention data, which are those symbols here, then we can see that deuterium retention is the lowest in the porous tungsten, then somewhat higher in the columnar tungsten, and in terms of tantalum or tungsten substrate, this almost the deuterium retention is comparable. Then some of the samples were exposed to pure deuterium only, and some were exposed to deuterium seeded with nitrogen. And the nitrogen data are marked red, and you can see that at least here where the deuterium is comparable between tantalum and tungsten samples, then you see no difference on deuterium retention with the nitrogen seeding. I also plotted here on the right side the average oxygen concentration, which I was having from the RBS data. And you can see that generally the oxygen level is more or less the same across all samples, except the porous tungsten. And maybe that's the reason that why the deuterium retention in those heavy oxidized samples is so low, but this is still something worth analyzing. While we are on Henny's samples, I would like to go to case 2, which is roughness and porosity. Previously, like a few years ago, we had this problem that RBS required only more or less flat samples. That was mainly due to the lack of the software, and we were not able to analyze samples which had roughness and porosity. but the software was since then improved, and I was able to utilize those features in Henny samples. So generally, we can experience two types of roughnesses. Here you can see this is a flat substrate, and then we have a rough layer deposited on the top of it. Or we can have a rough substrate and some layer deposited on that. Or we can have actually mixture of both rough substrate and a rough layer on it, which is actually the case of Henny's. So what Henny gave me, this is a tungsten, porous tungsten sample deposited on molybdenum. Initially, the porous tungsten layer was flat. Only the molybdenum sample, molybdenum substrate, had a little bit of roughness. But due to the exposure to magnum plasma, the porous tungsten layer also became rough with a different roughness degree than for molybdenum. And so I was able to measure this roughness and the porosity. Here on your right side, you have a spectrum. Like the red data is the measured data, and the blue line is the fitting, the simulation. And if I don't simulate any roughness, then you can see that the simulation doesn't fit the experiment. And if I simulate with the roughness, I can perfectly fit my data. And generally, the elements of the spectrum which are telling me that there must be some roughness is the incline of this slope, incline of that slope, then the fitting of the molybdenum substrate, and definitely this dip is also telling me that there must be some roughness in Henny's samples. So just so you don't get me wrong, this is not a tool to precisely measure roughness and porosity. I can just more or less tell you that there is some, and but it's just don't think like I could use that tool to measure this stuff for you. I can include it in my simulation if you have such samples, so then just simply you don't have to worry about that your samples are not flat. Okay. Then just to show you a little bit, let's talk about the depth resolution. So I told you that RBS can have really high depth resolutions, even down to 5 nanometers. This is a case which firm Alnobig gave me. This stuff was measured at our facility. So what we have here, we have a silicon substrate, and then we have layers of titanium oxide and silver deposited on it. And this sample was analyzed using RBS. And you can see here the pink signal is the silver signal, and you can see for peaks they correspond to each of those layers, where here most on the right you have the most top layer, and here is the most bottom layer. And then you can see 4 peaks for titanium. Again, here you have most top layer, here is the most bottom. And then we can even see oxygen from the titanium oxide on the top of the silicon substrate signal. And you can see those layers, the thickness of those layers was usually between 40 to 50 nanometers. And we can easily distinguish them. And quite frankly, if they would have been even thinner, we would have been able to resolve them as well. So then is of course also the question of mass resolution for RBS. The general thing is the higher energy you use of your incoming beam, the better mass resolution you can have. So this is shown on an example when we have SN contamination of the top of 2 nanometer ruthenium. And I think this is the research which Shichi is performing. So you can see that there is only 6 mass difference between those 2 elements. And this sample, this is now only simulation data because I cannot show you the real data. But here you have simulation for 2 MeV helium beam. Then you cannot distinguish those two masses, then you have 3 mega electron volts helium, then you can start seeing some SN on the top of ruthenium, and for 4 mega electron volts for helium, you can clearly see SN on ruthenium. So the general problem with the singletron, that's that I told you, that we can use maximum 4 mega electron volts beams. So in our case, there is some limit to the mass resolution, in terms of mass resolution, what we can do for you, because simply we cannot go for higher energies than that. But then if some of you have samples with elements of similar masses, then it's just come to me. I can perform simulations for you before starting measurements, and I can tell you whether it would be possible to distinguish those masses or not. Okay, then we also use resonances. What are resonances? Simply we use the fact that certain cross sections are generally flat and have resonant nuclear reactions, as it is shown here on the left side. Here you see cross section for the for helium-16 oxygen. So generally it is a flat cross section, and then the peak shows up at around 3.1 mega electron volts energy for helium. And so you can use those those are like very narrow needle resonances. You can use them for depth profiling of thin films at a very high depth resolution. In this case, even like 20 nanometers if you would have some oxygen in silicon. So when is the case where you could use it? For example, if you would have some silicon substrate, then a very thin layer of oxygen and some, let's say, gold on the top of it. So this could be, for example, a case when you are trying to engineer some new sort of material. And then you are asking yourself, is this oxygen layer located precisely at the depth at which you would like this to be located? And is the amount of oxygen exactly this what you would like to have for your newly engineered material? Then is the technique, the resonances can be used to answer your question. To show you an example here in the middle, we have just some spectrum. So these are counts versus energy. This spectrum was taken at the energy of 2 mega electron volts for helium. So there is no resonance used. And as you can see, you see no oxygen signal. But if you change to the resonance energy, which is 3037 kilo electron volts, then suddenly you start seeing this this oxygen, and it's you know, this is performed at a very exact energy, and you can see exactly where your layer is, oxygen layer is located, and how much exactly oxygen you have with very precisely. So if you have cases like that, then we can use resonances as well. This works for low Z materials up to mass 15 more or less. Okay, and then we have so-called forward RBS. I'm hearing some noises. Someone should be muted. Okay, so we have so-called forward RBS, which should be, since there is no backscattering, but our beam goes simply through the sample, then it actually should be called RFS. And this technique is used if we deal with membranes. So this must be very light and thin material, so the beam can pass through, and the detector is located just behind your sample. Here, this we really use in reality. I cannot show you the exact case because this was done for ASML, so I constructed an artificial sample. I constructed a membrane when we have layers of iron and boron, so iron, boron, iron, boron. Then in the middle we have some silicon, and then again we have iron, boron, iron, boron. On purpose, I used different isotopes of iron and boron, so we can clearly see which are the top layers and which are the bottom layers. And so here we have this sample we measured with RBS. And okay, you can see that we can distinguish between the top iron and bottom iron, but you don't see two layers. You just see one layer each for top and bottom. Then this signal is our middle silicon. And here we have signals from top and bottom boron, and they are overlapping. So when we use normal RBS for it, then generally we have a very poor depth resolution for those elements in our membrane. If we, however, switch to forward scattering, then here you can see our front iron, and you can see like two peaks here on the top. So we can distinguish those two layers in our frontal iron. Then you can have then we see our back iron, and again you can see two layers. So those two here, we can distinguish between them. Then we have our silicon in the middle, and then you can see here you can see the back and front boron, and again there are small, at least some dips in it. And so you can distinguish those layers as well. As you can see in this example, we are dealing with layers which are 10 nanometers thick. So there are very, very thin layers, and you can see them with the forward scattering because of such a good depth resolution. So if some of you is dealing with membranes, this is definitely a technique which you can use in your case. I see a question. Marco, what's the question? Hello. Moment.
Sorry, I was muted. So
okay.
The question is, what is the physical principle? Why is there a difference between backward and forward scattering? Is this loss of energy of the ions?
So this everything, well, it's a little bit now difficult to explain, and I plan to do it in more details when I have my detailed in-depth physics seminars. But generally, well, so when you consider this entire system, when you have to calculate the RBS system preserves the conservation of energy and momentum. And when you solve equations for it and you calculate so-called a kinematic factor, which is the ratio of tells you simply what is the energy loss between the incoming and backscattered beam, then analyzing that equation exactly from that physics, you can see in terms of the energy loss that the best depth resolution comes exactly for the forward scattering, which however usually is not used in most laboratories because usually people don't deal with the thin membranes. So usually detectors are located not just behind the samples but somewhere in front of it. But yes, it all deals with the at the end it all comes down to the loss of energy and momentum. But I will have more explanation in depth in my seminars, in-depth physics seminars, which I want to offer in the future. Okay, I saw Richard was happy, so I progress. So I showed you now 6 cases for ion beam analysis, and now I would like to show you 2 cases for ion irradiation as well. So far, we haven't performed any ion irradiation at all at our facilities. However, this is possible, and I got 2 inquiries from 2 different groups, and actually I would like to discuss those groups, their cases. They asked me whether this kind of irradiation would be possible at our facilities. So a TUE group came to me. They are dealing with field programmable gate arrays. And the problem is with those arrays when they are installed, for example, in airplanes or international station, ISS, that they experience failure, so-called single event upsets, and those are this already have been observed about 50 years ago, and it was concluded that those failures in FPGAs are caused by the cosmic rays. So simply cosmic rays, which are generally protons and atomic nuclei, are passing through the electronics and are causing defects there, which then lead to the failure of those electronic parts, which of course it's not acceptable because it can lead, for example, to an airplane crash, right? So this is something what you would like to avoid. And the different manufacturers have invented various mitigation techniques for those SUEs, and of course they would like to now test their FPGAs and their solutions to see if they really work. So they came to me and they said, can we use your ion accelerator to simulate the cosmic rays? So I compared both cosmic rays and the beam from the singletron to be able to answer the question. So cosmic rays are mainly protons with very high energy. Minimum energy is generally around 1 gigaelectronvolts plus multiple orders of magnitude. As you can see on this plot, it can go up to 10 to 21 electronvolts. So if we consider this energy 1 gigaelectronvolt, then the penetration of this beam through silicon is 1.7 meters. So this is a very high penetration depth. The fluxes of the cosmic rays are very low, but they generally depend on the energy, and they get even lower with higher energies of the cosmic rays. Generally, the amount of those upsets observed in those gate arrays are just 1 upset per month. So it is a very, very slow rate. And the amount of deposited energy by a particle in such a gate is around 10 of those units. And then, then was the question, can I simulate similar conditions using accelerators? So if we use protons, and the maximum energy of protons, which we can use in our case, are 3 megaelectronvolts, then the penetration depth is only about 100 micrometers in silicon, which is way, way less than compared to the cosmic rays. But the thickness of those gate arrays is also of the same order of magnitude. So about this, we don't really care about 1.7 meter. This is not very important. It's important that we can probe, with this depth, we can probe the important electronics in the gate array. So this is a sufficient penetration depth. Then our flux, if we go for a very low current, this is already very low current for us, the flux of our protons is 7 orders of magnitude higher compared to cosmic rays. The question is, is it good, is it bad? In this case, it's very good, because with such a nice high flux, we can simulate about 4 upsets per second. So this is of course beneficial, because no one wants to sit for months to observe those upsets and to check whether the mitigation techniques are working. You want to really have many upsets per second to quickly be able to test your mitigation techniques. So yes, this is very desirable and of interest for the groups. The only question is, our deposited energy, the amount of energy we deposit in those arrays, is about 2 orders of magnitude lower than in terms of cosmic rays. So, but apparently this is also not a problem, because I found also research when this amount of energy deposited is enough. So yes, in essence, we can do it. The TUE group can come to us, and we can check whether the mitigation techniques which they apply to their gate arrays are working in a very fast manner. So yeah, they are welcome to come and do research with us. Another case, another very obvious, is a plant mutation, and this is also was an inquiry by one of the Dutch plant producers. He read a paper about irradiation of ornamental plants in Japan, and he was asking me whether we could do the same for them as well. So generally, the objective here is to use ion irradiation to change the color and texture of ornamental plants. And what the group in Japan did, they used plant stems and irradiated them with 220 mega electronvolts carbon ions. The penetration depth of those ions in the plants was about 1 millimeter. Here is the deposited energy, and they used certain ion dose to achieve the effect. And the question was, of course, can we reproduce those conditions? Well, we don't have such high beams, so we had to use much lower energy. We don't have carbon, so I simulated this case with hydrogen. The penetration depth is only 150 micrometers. Now the question is it enough? It turns out that it is, because in order to change the DNA of a plant, you have to irradiate only the most outer layer, which is called epidermis. And this is this gray layer here. Here you have a cross-section of a plant. And the most outer layer of cells, this is the epidermis, which needs to be irradiated, and it's very thin, and it's enough to change the DNA of those cells in order to change the color and texture of the plants. It turns out we can deposit with hydrogen, low energy, we can deposit the same amount of energy as 220 mega electronvolt carbon. This is very important, and those values are comparable. And we can also achieve the same fluences as in synchrotron. Very quickly, in fact, we can do it, which means that a centimeter square of a plant, it's enough if we implant it for 1 second, and then we can shift to another plant. So this is a very quick experiment. Yes, we can do it for them. At this moment, they are a little bit less interested in that sort of experiment, mostly because the Dutch plant manufacturers are hit by the coronavirus, but I think this is something where we will come back to in the future.
Beata, there's another question,
Sure.
And the question is the damage in these FPGAs dependent on the energy of the cosmic rays?
Generally, no. Or rather, yes and no. So if I would calculate the damage profile for those cosmic rays at various energies, it would look generally like flat, 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 and a peak at the end of the energy. So for the very flat part of the damage profile, the answer is no, and for the end of the damage profile, the answer is yes. However, because those penetration depths this is like huge penetration depth, so actually in this case, and the field arrays are very, very thin, so let's say if we would have this profile like that, then the location of the gate array would be in the beginning of this profile, so in the flat range. So in this case, the answer is no.
Thank you.
Okay, can I proceed, or are there more questions?
No, you can go.
Okay.
Oh, sorry. Is this the same reason as why protons are used for therapy? They have a very local deposition of energy.
Yes, I think so, yes.
Yeah, I think with protons you can even use the Schrödinger equation to tailor where exactly you want to have the optimum deposition.
Exactly.
They can really have a zero deposition, and suddenly all protons are deposited at the location of the tumor.
Exactly.
The problem is also there that if the physicist gets it wrong, all the protons are deposited next to the tumor, which is a danger.
That is true. That is true. Yeah, but it's also, and it's not maybe that the physicist gets it wrong, but it's simply the penetration of the depth depends on the density of the material. I calculated my for the plants, I calculated penetration depth in water because plants are mostly composed of water. But you know, if you have anything on the way in terms of human body, some skin or other tissues, that will change the density, most likely will increase it, therefore the penetration depth will be shorter, therefore you will be hitting some tissues before the tumors, so healthy tissue, not the tumor itself. Okay?
Thank you. There's a comment from Wim Arnold. It is not the position where the protons are deposited, it is the damage that they make for the end of their path.
That is true.
Thank you, Wim.
Okay, so now I'm just coming to my summary. I told you my primary object for this presentation is to interest you in the facility. So feel free to come to me at this moment, rather call me or write me an email and share your research problem with me. If you are interested in the element depth profiling or material composition, or you would like to find out about your impurities, their location and amount, or you want to trace isotopes in your material, check roughly for porosity and roughness, or you would like to introduce some defects, modify your material, introduce defects or introduce some dopants, then come to me and you know I will be very happy to help you. I think in most of those cases, I simply have simulation tools, which, you know, I mean, I won't be able to probably to answer your questions just off the top of my head, but I have simulation tools to find the answer to your question. And most of all, I can find out what would be the best conditions of our accelerator of the experiment to answer your question. So, you know, I can do it for you. If you have this problem, please come. And if you don't come anyway, just to talk to me. So my plan is first to have one-to-one consultation with various people who think they might find use for the ion beam facility. Once I assemble a group of possible, researchers who are interested, then I would like to start a set of educational seminars. So I would start with basic physics, more advanced than this what I showed today, and then in-depth physics to teach you more. I would like to have seminars showing how to analyze data, how to evaluate it, and introduce you to different data analysis software. So that is the first plan. And secondly, also, once you come to me with your research problem, you also at the same time help me to design a better IBAS chamber, because I would like to collect research interest from you. At this moment, we have plans to have a new chamber where we can analyze small, light, and large and heavy samples, as large as, for example, tungsten tiles from ITER. We aim for no vacuum to ultra high vacuum with very slow pumping. Or slow and fast pumping. For example, slow pumping is needed if you would like to analyze, I don't know, a butterfly wing. It's very fragile, then you really need slow pumping. No vacuum is needed if you would like to analyze, let's say, piece of art. Then we want to aim for a sample holder which will allow for super fast or slow movement. For example, the super fast movement could be used in those plant mutation experiments where I need 1 second of implantation per square centimeter of a sample, and then I would like to be able to quickly shift from one sample to another. We want to perform high angular precision measurements with 5-axis goniometer for RBS channeling. Then we aim for temperature measurements at various temperatures, from cryogenic to very high. Usually temperature has a high influence on defect mobility. So this is something I'm aiming for as well. We want to have varying beam sizes, and generally also I would like to improve the accuracy of our measurements down to 1%. So even if you don't have ideas for our new IBS chamber, that doesn't matter. If you come to me with your research problem, I will take ideas from you. You know, you are not even aware, but I will have it from you. So please come share your research problems with me, and we'll be happy to help you. And yes, thank you. That's all.
Fantastic. Thank you so much, Beata. First and foremost, we want to thank you for your presentation, but also I want to congratulate you with the progress that has been made in your research. Is really fantastic what has been achieved in such a short period.
Thank you.
Having said that, I see also lots of smiley faces with applauding hands coming along. There are some questions that pop up. First, there is Eric Langerijs. He has a question out of general curiosity. He wants to know, for operando studies, what is the typical time resolution you're able to probe with the IBF? Basically, how quick is your measurement, and does this relate well to the typical rates of plasma surface interaction processes at pilot upgrade conditions? Or should you really tweak the experimental conditions to fit the most suitable IBF ions to be used?
Yeah, I mean, so, well, generally we are planning to measure continuously, but we can, of course, also take data or collect data in fluence increments. So we are aiming for a flux 5 to 23 deuterium per square meter second in UPP. So one can easily calculate how many seconds you need to reach a certain fluence, and generally that means that our measurement rate is faster than the flux. So we can easily measure this. This is not the problem in UPP. We have other problems, but this is not that.
Okay, that's good. Then Thomas, he wants to know, to simulate neutrons, what level of DPA could we create, and to what depth in, for example, tungsten using protons?
So, so in tungsten using protons, I cannot say on the top of my head. I would have to calculate it, but I would say in terms of depth, we could go around possibly maybe like 6 to 10 micrometers for the 3 mega electronvolt protons. And where do I have that table? Okay, here I calculated for 3 mega electronvolts protons, but that was, I think, calculated for carbon. Then we can go up to 150 micrometers. And the DPA rate, that depends on the DPA rate, which depends on the current. But generally, with current 40 microamps, it would take, based on my previous experience, about 2 days to reach 1 DPA. Continuous 48-hour implantation.
Okay, thank you so much. Then there is a question from Henny. Will you be able to measure the D/H content ratio, I think, yeah, in the very surface during plasma surface interaction in UPP, supersaturated layers, ERD with depth resolution of less than 5 nanometers in the future?
So generally, so yes, indeed, you have to use ERD for those if you want to measure deuterium and hydrogen simultaneously. Then it would be indeed also a shallow depth. Generally, yes, we plan to have ERD at UPP. However, well, we are at the moment developing still UPP, and we aim first for RBA and NRA. So I would say not this year. Okay. Generally, yes, not this year.
Not this year, but we're looking forward.
We are aiming for it, yes.
Yeah. Then there is a question from Edwin. Is the ion beam analysis suitable to analyze qualitatively and or quantitatively possible in-depth oxygen, oxidized surfaces in solid materials like charcoal or metal species like copper?
Definitely yes.
Definitely yes.
Yes.
Okay, Edwin, if you have a concrete idea, go to Beata and discuss it with her.
Yes, happy to do it.
And then we have Wim. He says ERD must be performed with glazing incidence, maybe not possible in operando.
Well, we will see about that. I still am for that it might happen. Yeah.
Okay.
I think Wim withdrew his
In
comment.
fact, yeah, I was too slow. I'm an old man. He said, sorry, withdrew with that. It is possible. So that's good. Then, Beate, would there be extra potential to your system if we would extend it, for example, with X-rays?
Yes, I know what you are talking about. Yes, definitely. So it's the talk of the hard X-rays from HeartLight.
Yeah.
And I definitely keep it in mind in my, I envision it, for example, to be connected to our new IBA chamber. I know that it might take a couple of years before that HeartLight is working, but in fact, I will keep, let's say, an opening in my chamber for that facility.
But what would you be able to do with it?
Whatever can be done with HeartLight.
Okay, exactly.
So, but for example, they use it for, this is one application which was used by a PhD student of mine. It's a technique called EXAFS, which sort of measures the distance between atoms simply. And so when you irradiate a sample, right, then you create the defects. And in the beginning, before the irradiation, you have a standard distance between atoms according to the lattice of that of the sample which you have, and then it can be shorter or longer depending on the type of irradiation you did. And what she did, she first irradiated, in her case, uranium dioxide samples for fission applications. Then she went to a cyclotron to use EXAFS to see how the distance between uranium and oxygen change, and she could draw conclusions about the defect types available then present in the samples. In this case, if we would connect HeartLight to IBAS, we would be able to simultaneously create the defects and check for the distances, lattice distances. So this way, of course, what she did was reverse engineering, guessing what happened, and it's definitely better to do those things simultaneously to observe in operando changes caused by ion radiation.
Thank you so much. I look at the comment boxes. Is there any question that people would like to put forward? They have to do it now. I wait. I guess not. In that case, Beate, thank you so much. This was really a very good start. And I wish everybody a phenomenal Thursday.
Yes,
Thanks so much.
Thank you. Bye-bye.